Next, we introduced an integration technique called integration by parts. Previously, we have observed how some properties of derivatives translated into properties of integrals. That is, the linearity property of derivatives translated into the linearity property of integrals, and that the chain rule turned into the substitution technique for integration. Next, we will learn how to turn the product rule into the integration technique called the integration by parts. So let's start with the product rule that in terms of u and v can be expressed by the following formula. We apply the antiderivative to both sides and use the linearity of the integrals to split the integral on the right side into two integrals. Using the substitution, we can change the notation and get rid of x. Subtracting the integral of v du from both sides, we obtain the formula, which is called the integration by parts formula. However, we will be applying this technique as a procedure rather than a formula. So let's review the process to which we will refer as the integration by parts. Usually, integration by parts applies when the integrand is a product of two functions, frequently of different classes. We choose u and dv such that u is easy to differentiate and dv is easy to integrate. We differentiate u to find du and integrate dv to find v, and finally write the result with the hope that the new integral is easier than the original one. Let's do the following example in which we have the product of x and cosine of x. We rewrite the integrand and choose u and dv and integrate by parts by differentiating u to find du and integrating dv to find v. We apply the integration by parts formula and produce a new integral which is easier than the original integral. We simplify the expression to get the answer. Notice that if we rewrite the integrand and choose the alternative u and dv and integrate by parts by differentiating u to find du and integrating dv to find v, then the integration by parts formula produces a new integral which is not easier than the original integral and leads nowhere. This means that choosing the correct combination of u and dv is crucial to the integration process. It is possible that when one doesn't work, the other one does. However, when none of the combinations works, it's also possible that integration by parts is simply not the right technique for a given integral. Let's do the following example in which we have the product of x and the natural logarithm function. We rewrite the integrand and choose u and dv and integrate by parts by differentiating u to find du and integrating dv to find v. We apply the integration by parts formula and produce a new integral which, after simplifying, is easier than the original one. We combine the like terms to get the answer. Notice that if we rewrite the integrand and choose the alternative u and dv and integrate by parts by differentiating u to find du and integrating dv to find v, the integration process gets stuck because we don't know how to find the integral of the natural logarithmic function. Let's do the following example in which we don't have a product but have only the natural logarithmic function. We rewrite the integrand as a product of the function by 1 and choose u and dv and integrate by parts by differentiating u to find du and integrating dv to find v. We apply the integration by parts formula and produce a new integral which, after simplifying, is easier than the original one. We get the answer after completing the integration by parts. Let's do the following example in which we have the product of x and the natural exponential function. We rewrite the integrand and choose u and dv and integrate by parts by differentiating u to find du and integrating dv to find v. We apply the integration by parts formula and produce a new integral that is easier than the original one? We get the answer after completing the integration by parts. We discussed and practiced an integration technique called the integration by parts.